Hello, my name's David Themens. I work with the Canadian Higher Arctic Ionospheric Network at the University of New Brunswick in Canada. I'll be talking to you about the ionospheric modeling capacity that we have at the Canadian Higher Arctic Ionospheric Network, or CHAIM, and a special shout out to the modeling team that we have at UNB right now, namely Chris Watson, Ben Reid, who have contributed significantly to this talk, as well as Anthony McCaffrey and Joey Bernard, who help maintain a lot of the systems I'll be talking about today, and Jay, who runs our lab. So to give you an outline, I'll start off with an introduction to the empirical Canadian Higher Arctic Ionospheric model, E-CHAIM, before getting into, describing the database that we use to drive that model, and going over some validations that we've done over the past year or two since the model's been released. I'll then talk about a new feature that we have in the model, namely an auroral precipitation scheme for the E region, and some other assimilation-based modeling products that we've made available to the community on our website, namely a near real-time assimilation system called E-CHAIM, and a reanalysis data assimilation system called R-CHAIM. I will mention that this talk is a little bit longer than I would normally do for this, so feel free to skip ahead to the newer parts if you're already familiar with E-CHAIM. So E-CHAIM is an empirical model of the high latitude ionosphere above 50 degrees north geomagnetic latitude. It models electron density in a fully 3D sense, and it was designed as an alternative to the use of the International Reference Ionosphere at high latitudes. The model was built on probably was the most extensive data set ever assembled for this type of empirical modeling effort, with over 26 million observations for just the NMF2 model alone, and the various other observations used for the various other components of the model that I'll talk about in a minute. So E-CHAIM was developed and published over a course of 3 papers. This 2017 paper that described the F2 peak of the model, so HMF2, or peak height of the ionosphere, and FOF2, the peak critical frequency of the ionosphere. The 2018 paper described the topside portion of the model, which was based loosely on what's used currently by the International Reference Ionosphere and any quick empirical models, but with some fixes to accommodate some fairly significant issues with those models. Finally, in our 2019 paper, we finished the model by including a E region, or bottom side and E region, which performs comparably to the IRI, but in that paper we also demonstrate that there's definitely a need, obviously, for the inclusion of a auroral E region in the model. So to give you an idea of what E-CHAIM looks like, at least horizontally, these are just some plots of the FOF2, the peak critical frequency of the ionosphere, from the IRI and E-CHAIM over the E-CHAIM domain. So the dashed red line here marks the absolute lower boundary of the model, and the solid red line here marks the recommended lower boundary of the model. We generally provide output in these extra 5 degrees here, mainly to allow users the opportunity to merge the model with other models or non-regional models of their choice. So give them a bit of a buffer. As you can see, E-CHAIM, it's a regional model which allows us to capture an better elongation of the mesosphere trough, which really is not available in the IRI, as well as the presence of an auroral F region ring here, as well as a polar hole, which again is not available in the IRI. Otherwise, as you get to lower latitudes, the two models look fairly similar, aside from a little bit of a lower electron density from E-CHAIM than the IRI on the day side. In terms of the vertical structure of the model, E-CHAIM models electron density as a function, or as these, or a single layer based on these Epstein functions, or I guess a hyperbolic secant squared layer that's anchored at HMF2 and NMF2, or the peak density and peak height of the ionosphere. And then off of that, we use, I guess, vertical structuring of the scale height, or the scale thickness of the ionosphere as what we actually model. So we do that because for most HF communications users, HF is very sensitive to, I guess, subtle curvatures in the bottom side electron density profile, and least squares doesn't so much care about subtle curvatures, it cares about bulk differences. So if you were to fit an electron, or this electron density profile here to a function, you could easily obtain this very good least squares fit with you know, a linear bottom side for that matter. Whereas if we, instead of trying to fit this in terms of electron density, we translate this into a scale height domain, which is given down here, you can see that these subtle curvatures in the bottom side become exaggerated curvatures in the scale height. And because these curvatures are more exaggerated in the scale height domain, it's easier to, I guess, more adequately model them by use of simple least squares fitting. So E-CHAIM uses, again, is anchored at MF2 and HMF2 with a, I guess, a constant scale thickness associated with the F2 region, as well as these two functions that define the F1 and E region peaks in the scale height domain. In the top side, we use a function that's effectively linear near the F2 peak, but becomes asymptotic at high altitudes. All of this requires to be driven by various indices, and we use F10.7 flux for our solar driving, as well as AE index, AP index, and DST, as well as PC index for driving geomagnetic activity in the model. And so to facilitate, I guess, the use of this model without having to manually grab all these indices yourself, we provide a SQLite database of these parameters on a daily basis that's updated every morning at 8 a.m. Atlantic time. In fact, you don't even need to go to our website and download them. You can simply just use either the update keyword or function, depending on the distribution of the model you're using. They'll automatically update your local database with any changes that have been made to the database that we have at UNB. Of course, the source code for everything that I'm talking about in terms of E-CHAIM is available on our website for free use by anyone with the source code in MATLAB, IDL, and C. So since the release of the model, we've done a number of validations. Here's just an example of one against DMSP in situ observations around 830 kilometers altitude. Overall, E-CHAIM was found to be able to provide electron density at these altitudes at about 30% improvement over the IRI. And you can check out this paper if you're interested in those results. To give you an idea of what that kind of looks like, these are, I guess, monthly median or monthly versus MLT binned electron density from DMSP, E-CHAIM, and the IRI above 70 degrees north geomagnetic latitude. And you'll note that the IRI tends to significantly underestimate electron density at these altitudes and in the polar cap, whereas E-CHAIM does a very good job at capturing the solar cycle, seasonal, and diurnal variability in this region. We've also looked at total electron content, where the black line here is the RMS air from E-CHAIM and the Canadian, from a series of Canadian GNSS receivers. And the red is the the RMS error associated with the IRI, and you can see we're doing very well into the polar cap and auroral oval, with errors really converging to those of the IRI or slightly worse than the IRI at subauroral latitudes. We've also done comparisons to swarm. Just to give you an example, this is overall electron density from swarm, MLT, and magnetic latitude for 2014 and 2017 from swarm here on the left, E-CHAIM in the middle here, and the IRI on the right. And you can see qualitatively E-CHAIM captures the structuring that we see in the swarm observations. But you do see that there is a tendency for us to underestimate electron density at subauroral latitudes or near the lower boundary of the model, which is consistent with the total electron content observations we saw before. Now, I mentioned that we've recently released version 2.0 of E-CHAIM that now includes a precipitation E-region model, which was originally developed by me and Dr. Chris Watson at UNB. We had a number of restrictions in how we need to set this up, namely because these empirical models, one of their claims to fame is that they're computationally efficient. And on top of that, we've made the mistake of providing the code in 3 different source code languages. So we kind of tied our hands in terms of what we could do in terms of adding on a precipitation code to the model. So we had to build something in-house, which leads us to doing your standard assume photochemical equilibrium, where we can write the electron density in a perturbed or precipitating environment to the quiet E-CHAIM electron density, this auroral ionization rate, and then this effective recombination rate. We've used Gledhill 1986 empirical effective recombination rates as a simplified representation of the recombination that we need. And for our ionization rates, we've used a Fang et al. 2010 based precipitation scheme with a Maxwellian energy distribution that is driven by mean energy and flux, either measurements, in the case of, I'll show you some examples using SUSY and Goofy inferred data, or from our model, which I'll discuss in a few minutes. So if we take mean energies and fluxes inferred from DMSP SUSY optical observations, we can go from the blue, here's the standard E-CHAIM ionosphere at Poker Flat for a certain precipitation event. The black is an incoherent scatter radar electron density profile during this time, and the dashed red line is what we get from our precipitation scheme when we used measured, or not measured, but I guess optically inferred mean energies and fluxes. And you can see in general, if we get the energies and fluxes right, we can do a pretty good job at capturing the electron density enhancement in the E region associated with these precipitation events. So to get those main energies and fluxes, we don't do anything particularly fancy. We've got all data that we have from Goovy and SUSY inferred mean energies and fluxes. And we've just binned it in terms of AE index into these MLT and geomagnetic latitude grids, where the AE bins are on the bottom here. And this is just an example of the 200 nanotesla, 250 nanotesla AE bin for mean energy and flux. Generally, we get qualitatively what we would expect. All in all, this is a very similar scheme to what's done by the Zhang and Paxton model, or Zhang and Paxton 2008 model, except we have a little bit higher time resolution because we've opted to use A index instead of KP index, and we've made no assumptions about the shape or the horizontal distribution of the energies and fluxes, which in the Zhang and Paxton 2008 model, they do use parameterization. On the right here in red is the Zhang and Paxton mean energy and flux. Top is energy, bottom is flux. For 0 MLT and 60 degrees north geomagnetic latitude. The black is the same thing, but from the E-CHAIM model. And what you'll notice, the big difference between these two is that E-CHAIM doesn't have that spatial smoothing or that temporal smoothing that we see in the Zhang and Paxton parameterization. So we're able to get a little bit more time resolution out of the scheme that we've done, but ultimately they look quite comparable, or at least qualitatively so. So implementing this mean energy and flux model and testing against some poker flat increment scatter radar data. The left here, sorry, is the data from the poker flat increment scatter radar, and the right is the corresponding E-CHAIM electron density, where you can see a number of precipitation events in both of these, both the data and the model. Generally, E-CHAIM does a decent job at least capturing the heights and vertical distributions of electron density during these precipitation events, although you can see that generally we do underestimate the electron density a bit, and that probably comes from the fact that we have a spatially smooth and also, again, temporally smooth model. So we're blurring what are generally fairly small scale structures across larger scales, and so we're left with a little bit of averaging underestimation. But ultimately, qualitatively, we're doing pretty well, at least capturing the events that we want to capture and providing E-CHAIM with the long missing auroral precipitation or auroral E region that it needs. For that particular reason or period, the red is the E-CHAIM errors or RMS errors in electron density with respect to the poker flat increment scatter radar without the precipitation scheme, and the black is with the precipitation scheme. So you can see, in general, there's a significant improvement in our performance by including the precipitation scheme, and there are likely a number of improvements that still need to be made with that scheme, but it gives at least the model an auroral zone for the first time. In addition to E-CHAIM, we also have the assimilative Canadian higher ionospheric model, or A-CHAIM, which is a near real-time data assimilation system that was built predominantly by Benjamin Reid, who's a PhD student working with us. And what we've done was we built a sequential maximum likelihood estimation scheme, which is effectively just a particle filter with a highly nonlinear basis set that we've used to try and accommodate for the fact that we have very sparse data at high latitudes that can cause problems for traditional data assimilation systems. In order to reduce the size of our basis set as much as possible, we've also parameterized the vertical in terms of the same functions that we use to define E-CHAIM's vertical structure. So instead of having voxels, we have nonlinear spherical cap harmonics for our horizontal basis set, and the E-CHAIM parameterization of 7 parameters to define the vertical structure. We've also used E-CHAIM as a background model to give us an initial guess. And currently we assimilate all ground-based GNSS, ionosonde, increment scatter radar, and JSON altimeter data that we can get in real time or near real time. To give you an idea of how that works out, we did a few tests where we've restricted we went back to a 2017 geomagnetic storm. The superstorm occurred in early September 2017. Excuse me. And we effectively just gathered all the data that was available at that time and restricted our simulation data set to only those sources that would be available in near real time. We then do the assimilation run and then test the assimilation system against all those stations that were available now, but wouldn't have been available in near real time when the assimilation system would be run. And so the top plot here is a time series of the overall RMS errors in slant electron content from the background model, E-CHAIM in black, and the assimilation system in blue or red. Where you can see in general, the assimilation system, great, is being the background, that's what we hope. At all of the data, or at all of the locations where we don't have, or where we're not assimilating data. The bottom plots here provide the MLT and magnetic latitude distributions of those, or of the differences in error between the background model and the assimilation system, where blue means that the background model is improving upon the assimilation system is improving upon the background model, and red vice versa. So the storm takes place during this September 7th through 9th period in this second figure here. This figure here is for September 2nd through 7th, which would be the pre-storm period, where you can see in general there's an improvement by the assimilation system at subauroral latitudes, which is actually quite nice because that's where, from the study that we did previously on the validation of E-CHAIM, where we expect the largest errors in E-CHAIM's representation of electron content. As the storm begins, you can see further improvement upon the background model by the assimilation system. And then the recovery phase, we start to see still improvement around this noon sector at subauroral latitudes, but in general, we start to kind of converge to the background model. And if you notice at the top here, you start to see a little bit of red towards into this post-storm period. But ultimately what that is not so much that the assimilation system is getting worse, but rather that the background model has actually started to perform quite a bit better, such that we're really reaching the statistical limit or the error or noise limit of our observations. We also have the reanalysis Canadian High-Arctic Ionospheric Model, or E-CHAIM, which gathers and assimilates all available ground-based and spaceborne GNSS data. That's Swarm, Gauche, Cosmic, Sentinel, Champ, Grace, everything you could think of. If it was in space, it's in here. All in situ satellite measurements, all altimeter measurements, ionosomes, and incoherent scatter rate errors automatically gathered and assimilated into the system. The system is now available for open use by the community. You're welcome to click this link to try it out. If the period that you want isn't in the list that's provided at the top of the page, just input the period that you're interested in into the form at the bottom, and you'll receive an email once that run is done. The output is provided in a SQLite database of coefficients that require a C or MATLAB tool that we've developed to interpret. We provide that tool again freely or for your use in the software downloads section at the bottom of the E-CHAIM page. So just a summary, I guess, E-CHAIM is now freely available online at the link there. And the assimilation system is also online and running, running in near real time at the moment at the link provided here. We provide distributions of all of our source code for E-CHAIM in C, MATLAB, and IDL, as well as we provide a web interface similar to what's available for the International Reference Ionosphere. Thank you for your time, and thank you to our funding sources for this work. If you have any questions, feel free to send me an email or provide a comment on this video. Thank you.